Thanks, Andrew. All right, so I'd like to start off by inviting you all to carry out a thought exercise. So imagine that you could time travel 5 years into the future. You could pick any quantum hardware developer of your choice, and you get to ask them one question. What would that question be?
What is the most valuable stock?
You stole my punchline. Yeah, no, I'll give you a moment to think about it. Okay. Yeah, I'd like to hear. We can talk about what they are later. I'm genuinely curious to hear. Of course, the question that you came up with certainly depends on what your objectives in quantum computing are. You know, if you're a hardware developer yourself, you might ask a very different question than if you are, say, developing quantum algorithms. Personally, in my role as an evaluator of quantum technologies at Apollo, I was trying to come up with a question where I could gauge what challenges that hardware developer might be facing. And I think it's not too controversial to guess that likely a major challenge for them will be trying to scale up their system, build larger systems. You know, likely a characteristic of this early fault-tolerant quantum computing regime. And yeah, I guess to raise the stakes a little bit with that question, you know, it's not just me who's interested, you know, not just, you know, among us. There are real resources going into trying to evaluate, you know, what are the scalability challenges among these different quantum hardware developers. So for example, there are a number of recent government programs putting real resources into trying to answer that. Okay. So what is the actual question that I would ask to get at what are the scalability challenges a hardware developer might be facing? So I would ask, how does error correction performance depend on system size? And the goal of this talk is to motivate why I think that's a useful question to be asking. Also, I believe that there are a number of people in the audience who have thought way more about this question than me. And so I'm really interested to get some more conversations going around how other people think about scaling quantum computing technologies. Okay, so before getting into gauging progress or evaluating progress, I want to first anchor this by talking about what are these targets that you're wanting to evaluate progress towards. So I imagine that some of you, or I know that some of you are very familiar with this so-called quantum benchmarking graph. Many of you contributed points to this. This is one of the outputs of the recent DARPA quantum benchmarking program. You know, one of these programs aimed at evaluating progress in quantum computing. And to orient you to this plot, it shows each point corresponds to a different application. And the vertical axis is the number of operations that would be required, you know, making many assumptions about algorithms and compilation to run that, to address that application. The horizontal axis is the number of logical qubits that the system would need to provide to run that application. So yeah, maybe for what it's worth, you might be, your eyes might be watering a little bit looking at some of these points that are hanging out around Avogadro's number up there. I'm actually very proud of those. Those were coming from some of the collaborations I was a part of in this quantum benchmarking program. To set an anchor for the discussion, though, I'll pick these more favorable looking points, in particular this homogeneous catalysis, GSEE, which is coming from work led by Nicole, and a number of people out here were involved in that. So the number of operations is roughly, I think, 10 to the 13, and about 2,000 computational qubits are required. Okay, so for tracking progress towards hitting a target like that, we need a bit more information. So this is still talking about logical requirements. There's a remaining question of, well, if I'm trying to build a system to meet those requirements, how many physical qubits will I need? How low do I need to get my error rates to be? So how is that process done? So I'm just going to overview an approach to doing this at a fairly high level. This approach is referred to as quantum resource estimation. Right? A big part of Katarina's talk was discussing quantum resource estimation. And it can be used to predict target physical requirements given some target logical requirements. So as a first step, just to set this broadly. So in order to run these quantum computations that have many, many operations, and in order for throughout the quantum computation to have the chance of it failing to be, say, less than 10%, it requires each of those operations to fail no more than a very, very, very small number, roughly the inverse of this number of logical operations. And the tool, the most promising tool for realizing those very small logical error rates is quantum error correction. So the cost in terms of physical overhead depends on how much quantum error correction overhead is needed to reduce the logical error rates to the targets. So how do we determine what that quantum error correction overhead is? So I'll just take a specific example of the surface code and walk through how this is done. So the goal is to understand, given the physical resources for, say, a single surface code patch, what are the corresponding logical error rates? So in the surface code, the logical error rate is governed by how big of a 2D patch of qubits is used to encode a logical qubit. So in this example, this is a 5x5 patch. The width in the square patch corresponds to the distance of the code, meaning you'd need at least 5 distinct errors in order to cause a logical error. It has 25 data qubits. I think the data qubits are the black dots there, and 24 ancilla qubits. So 49 physical qubits are used to encode that single logical qubit. So how do you determine what the logical error rate is for, as a function of code distance? So the first step is you propose some error model. In order to make the simulations tractable, you have to choose some very simplified error models. And it's typical to you choose a single error parameter. Maybe you could think about this as corresponding to the probability of any X, Y, or Z error occurring after each gate. Then you carry out some simulations of D by D surface code patches, varying D, varying this error parameter to determine the logical error rate in each case. Then for all this data, you can fit this to an exponential decay model. And in this simple case, it tells you two parameters. One is this constant factor in front. The second is this p threshold, which is a key parameter in quantum error correction. This p threshold tells you the number where if p is below this threshold, then increasing the code distance or increasing the patch size will reduce the logical error rate. If p is above the threshold, then increasing d will cause the logical error rate to increase. I was recently thinking of this washing my hands in a gas station bathroom, where you go through all of the steps, you do everything you're supposed to, but at the end, you don't necessarily come out cleaner than you started. So it's kind of like this. Okay.
How is that related?
Have you been to many gas station bathrooms?
Right. Like why you say like you expect, like what's not meeting the expectation in this case?
Sorry?
What's not meeting the expectation in the surface code case?
Maybe I'll say a little bit more about it and let me know if this answers your question. I guess imagine carrying out a simulation of a bunch sequence of syndrome extractions in the surface code. They're giving you syndrome data. You use a decoder to attempt to correct at the logical level. If, for example, there was like a fairly high probability that having a chain of errors span the patch is going to happen, then the logical error rate that you get out could be very high relative to p. Maybe I don't understand what your
Yeah, I guess like were you saying like this model looks very beautiful but it doesn't work or something like that?
Oh, no. Just saying like what's a way to think about why if your error rate is too high, then error correction doesn't help you.
Oh, okay. I do see.
Not a great joke. Okay. Oh yeah.
Sorry, it might be a naive question, but like I was wondering why should we expect such a smooth decrease in the logical failure rate as I increase d? Because I would have thought, let's say d goes to 10, d goes to 9, would correct for the same, like the minimum weight error that is not correctable is the same for both, because it's like, the floor of d plus 1 over 2.
Okay.
So I would have thought increasing to even distances would be like very close actually to the odd distances.
Okay, so yeah, this is a little bit in the weeds. This is, I think, one of the conclusions of this particular paper, challenging this belief, or I guess some suggestions from earlier works where even code distances are not worth it because logical error rates are closely the same. I don't know exactly what their explanation for that is, but that's one of the findings in this paper that maybe Michael knows.
Yeah. I mean, the asymptotic gradient will be the same if you have a minimum weight encoder for those two cases, but the prefactor might differ. The number of min-weight failing configurations will be different. So even in the asymptotic limit, the distance 9 will be better than distance 8. But it'll just be shifted in the same gradient on a log-log plot, I guess.
Like they'll have the same slope asymptotically. Yeah.
So you're probably not seeing the asymptotically low p regime.
But that means to fit this, I would need a different A for the odd distances versus the even distances then.
Yeah. I have a strong guess that we're kind of sidetracking this off. But
Yeah, I think, that's, there might, I don't know, I was looking to see if there's a pattern in how well there's a fit between even and odd, I don't know. Okay. Yeah, I think probably a little bit in the weeds for this talk, but would be interested to talk more after. Okay, so now you have this model for the logical error rate as a function of physical error rate and code distance. Remember, our aim is to determine what the physical qubit overhead is. So you take the target logical error rate, you fix the hardware's physical error rate. You can think of that as like setting a horizontal line and a vertical line on this plot. And then you identify, what's the smallest D patch size that meets that logical error rate requirement. And then to get the total number of physical qubits, you scale the number of logical qubits by the number of physical qubits per patch. Okay. So in this way, quantum resource estimation gives some rough physical targets. So looking at the purple, it translates this logical target into some physical requirements. Assuming that you've fixed the error rate, it tells you how many physical qubits you would need. But it also can be used to go the other way. Given some characterization of a system, its physical error rate, its number of physical qubits, what are the targets that it is able to hit? So going on the blue, going from this blue dot, it points to a curve. As you vary the code distance, there's a trade-off between logical error rate and number of logical qubits. For the rest of this talk, I'll end up discussing that trade-off quite a bit. So happy to answer any questions about what I'm meaning there. Yeah.
Yeah. So if we going back to the first slides, I was just curious about what's the time overhead. You mentioned the qubit overhead.
Sorry.
What's the time overhead when you go from logical qubit to physical qubit?
Okay. What's the time overhead? So I won't end up talking too much about time overheads in this, but in the specific case of the surface code, this time overhead will be, and I guess Katarina discussed this. So, it'll be like in the surface code, you'll need D rounds of error correction per logical operation. So it'll be time per surface code cycle times the code distance.
Maybe 30.
Say it again.
Maybe 30 is the code
Oh,
distance.
and maybe the code distance is 30 for
Yeah. So maybe the overhead
applications.
is around 30
Yeah.
times the original code cycle time.
Yeah. Okay.
But if I understand this correctly, these are the contours on the QB plot, right?
These correspond to those contours on the QB
Okay.
plot. That's right, the
Everybody will get
staircases.
that, but-
I didn't draw attention to those, but on the
this
QB
is what
plot,
you're talking about.
you might have noticed there are these staircases. And these are, so, right, going from number of operations to logical error rate, we basically flipped the y-axis. So those descending staircases now look like ascending staircases. Okay, so there's something tantalizing about this plot on the right. It suggests a path to hitting this utility scale target, right? You're developing a hardware, it's like, okay, or you're trying to assess what progress a hardware system needs. It says, okay, well, you would need to advance this blue dot towards the purple star. And that gives some motivation for physical error rate and number of physical qubits as being indicators of progress and indicators of system performance. I think that is okay if we're keeping in mind that we're squinting and looking at very distant targets. However, and I'm going to discuss this quite a bit as follows, I think that picture falls short for the purposes of more fine-grained tracking and evaluating progress. Okay. So what are these shortcomings? Okay, maybe the most obvious is that these two physical metrics don't reward or track advances in quantum error correction. Or advances where some methods need to be introduced to, say, address leakage, which are very important. Maybe you could think of those advances as pulling the star a little bit closer. But if you're just tracking, that blue dot, it doesn't reward that. Second, and maybe more to the point, of course, there are many important error parameters that go into informing the performance of quantum error correction. So for example, in this recent Google Quantum AI Nature paper, there were 11 different error parameters that they considered. And many of these parameters are actually varying across the chip. So all told, given these chips of on the order of 100 qubits, there are many, many error parameters that are being tracked. And they all contribute to varying degree towards informing the performance of quantum error correction, at least in simulation. So the third point is that even with all that very fine-grained information, parameters that are coming from experimental data, all of those parameters are nevertheless insufficient for predicting logical error rate performance. So this is discussed in this Google paper. I think that, this is an amazing work. I'll probably say that multiple times. But this is shown in this plot here, where in order to account for the error suppression factor that they observe experimentally, they have to build in some so-called excess amount of error that isn't determined by any of the error parameters to account for the full extent of translating physical error parameters into logical error performance. Okay, so these parameters themselves are insufficient. And so thinking back to the question, I think it would have been reasonable at the beginning to be like, oh, hardware developer 5 years from now, let me know what their error parameters are and how many physical qubits they have. Which, okay, if you're aiming to do some coarse tracking, that might suffice. But I think it can nevertheless be misleading. James.
Another way to add, I'm going to rephrase this to make sure that I understand your point. Everything that's in color there is in their noise model for that device. So this is a model closure exercise to see if their model is accurate. So the excess noise is things that are not in their model of this device. And then the further point would be they need to understand that so that they could project what that would look like for bigger devices or more representative devices for the utility scale machine that they want to build.
Yeah. Good. Yeah, great point. Yeah, you could frame this as there's a question of model closure. How well are their models able to predict performance? And there's some gap there. Okay. Right, and that's important because in principle you're using these models to design these systems.
Maybe one question.
Yeah,
So Q, you're saying Q like number of qubits, is that what you mean?
Yeah.
But I think if you go back to your chart about, you don't have to go back, but the logical error rate scaling, right? The lambdas does affect that, right? Does affect which code you can use. So if the lambdas aren't as good as what you predict on that chart, then you need more qubits.
Yes, yeah.
So it crunches all those things together more and more, right?
That's right.
So that still is a metric that's part of this process, right? You substitute lambda in for that, you will see a number of qubits go up. So it's still, they're related, right?
Yeah, I agree. I mean, if I understand what you're saying, if you know what this experimentally determined lambda is, then that can go into informing the physical qubit overhead. Is that what you're saying?
Yeah. The logical error rate you can get with a particular distance code, which then determines your physical qubit overhead.
Yes. Maybe just push back on that a little bit. I think to an extent, right? This lambda, in practice, in this paper they find this, is code distance dependent, right? As they consider bigger patch sizes, the lambda actually gets a little bit worse. So right, just there's not a single lambda that captures, the
That's
ability.
right. Sure.
Okay. Okay, so if this P and Q are insufficient for tracking at a more fine-grained scale than what is. So I think this is also not so controversial, but I think logical metrics are a more faithful indicator of progress. Reasons being they are closer to being functional metrics, the things that would be required of a system. And at least in our in this talk here, they're in the same units as the original target that we determined. And so, from the beginning, you might have thought that a good question, I think it's a pretty good question, is like, hey, hardware company 5 years from now, what is your logical error rate, logical qubit trade-off that you have today? And the hope is that 5 years from now, that trade-off curve would be much better than it looks today. Okay, so for the rest of the talk, I am going to try to argue that the different question that I posed at the beginning might be more meaningful for assessing progress, or at least get at a different dimension than this question. Okay, so imagine the following. You're given some data from that hardware company 5 years from now. It shows their logical error rate, logical qubit trade-off that they're able to achieve. That's hardware developer A. Your friend happened to ask hardware developer B the same question, so they give you their data. And to compare the two, you see like, all right, yeah, roughly they are achieving comparable trade-offs. I think there's something that is not fully captured by this, which is, can we differentiate the ability of these two hardware systems to scale? Can we get some indication that one of these might be having more difficulty improving this logical error rate, logical qubit trade-off than the other? I don't know, I'm picturing kind of like if two people are in a race, if you look at a snapshot of it, they might look tied, but if you're looking at maybe more a video of it, you might see that, okay, well, this person's moving much faster. I think that's roughly the picture I have in mind there. Okay, so what would it look like if a hardware system was demonstrating good scalability? So I'm going to go back to using this P and Q plot for just illustrative purposes. So imagine that they consider two systems that they have today. One is a little bit bigger than the other. And you find that there's a proportional improvement in this logical error rate, logical qubit trade-off, proportional to the growth in system size. I would call this an indication of scalability, right? Scalability being that physical scaling translates into improved quantum error correction performance. Yeah, what's up, Lex?
So your original curves, right? You're looking at logical error rate as a function of number of logical qubits. Are you assuming a fixed number of qubits for this?
Yes.
I see.
Assuming a fixed number qubit, yeah.
Got it. Okay. Thank you.
Yeah, sorry, I should have emphasized that. So yeah, I'm really picturing like, each of these curves is like, there was a chip that was manufactured and experiments were run on that chip. Athena gave a
We can talk about it later. I would consider replacing qubits with dollars, because if your qubits are cheap, I don't care if you made 1 trillion of them, right? But anyways.
Okay.
Yeah.
But also, I think for a lot of the new architectures, there's not like a family of codes that you can
That's
use.
right. Yeah, so this is a good point. So these curves that I'm talking about, giving the illusion of this smooth trade-off, is pretty specific to topological codes, or say like surface code. Right, but there are, especially recently, more codes, that might be, of a fixed distance and fixed size. Yeah, I think nevertheless, there's still data that can be put on a plot like this. Okay, yeah, I guess if there was like, a single code, I'm picturing it's bicycle code, right? That you had in mind, and that was the target. No, I get, yeah. We should talk more about this later. I think this was maybe one of the subtleties I was thinking might come up. I'd be curious to know how you might think about gauging scalability in the case where you have, bicycle code as the target. Okay.
I would just suggest maybe flipping that around and asking the question of a family of codes. Like, okay, what are the requirements you want for, like, say, a QLBC family of codes that allows you to model it correctly in this way? Like, it has to scale certain sizes and certain distance so far, right? Like the analogs to what the surface code gives you. I think would be cool to do.
Yeah. Yeah. I think in general, you can come up with, some families of codes for most cases. Maybe some families will have much better trade-offs than others, right? Okay. Okay, so what does it look like in the case of limited scalability? I think it's characterized by bigger is not always better. So for example, it might be the case that in increasing, for the system of larger size, there's also a degradation in quality. And translating this into the logical error rate versus logical qubit number, there might be a corresponding bunching on this curve. So there's not an advance in this trade-off. So limited ability to scale entails the physical scaling not translating into quantum error correction, improved quantum error correction performance. Okay, so for the rest of the talk, Andrew, can I get a time check? 15 minutes left? Okay, yeah, for the rest of the talk, I'm going to actually probably just talk through one example of scalability, and if we have time, maybe get into a second. So the first is going to be talking about scalability today, going a bit more into this recent Google quantum error correction demonstration. And then if we have time, talking about scalability in the future, how this might inform thinking about quantum algorithm development and hitting utility scale targets. So again, yeah, I think this experiment was pretty amazing, and it's just great that we have this data that we can actually start asking these kinds of questions with, which I think when we were working on this FTQC perspective piece, we were really scraping the bottom of the barrel to get something like this. Okay. So back in 2023, Google had a quantum error correction demonstration published in a Nature paper where they showed that there's an eclipsing of this break-even point where going from a distance 3 code to distance 5 code, they're able to marginally reduce the single cycle logical error rate. Okay. On this plot, those basically look on the same line, but trust me, the d equals 5 is a little bit lower. So then in, the first bullet is still supposed to be 2023. It just changed. So then in 2025, for this same chip, I guess it was a 72 qubit chip in both cases, they showed that now in going from distance 3 to distance 5, on average, there's a 2x reduction in the logical error rate. Logical error rate per cycle, not logical step. And then, okay, can we use this data to gauge scalability? Or consider questions of scalability? Fortunately, yes. They also provided some data for up to a distance 7 code, for distance 3, 5, and 7 on a 105 qubit chip. So kind of that setting I was thinking of before, where you have a smaller chip and a bigger chip, and you can compare their ability to trade logical error rate and logical qubits. I guess maybe for where I'm getting this data, right? I'm getting the logical error rate straight from their paper. For the number of logical qubits, I'm fudging it a little bit. Basically, I'm imagining that I'm dividing the number of physical qubits that they have by the number of physical qubits per logical qubit. Okay. So for example, they weren't running I don't believe they were running the distance 3 surface code patches on the big chip in parallel. Okay. So what we find if we place this on this plane is that if it was showing very promising scalability, you might imagine just this horizontal shift where it's just bigger is better. What you see is actually it's not so bad. There is mostly a horizontal shift, but there's also some vertical shift. And I think this might indicate some of the challenges that they're facing as they're trying to run these error correcting demonstrations on larger and larger chips. Things having to do with being a little bit harder to manufacture. Calibration is harder as you have big chips. There are many reasons that I'm not expert in, and hope to have some more discussions around what those causes might be. And I guess the takeaway is I hope to see more experimental demonstrations that are giving some evidence that as bigger and bigger systems are being used for these demonstrations, there are proportional gains in this trade-off. Okay. Time check, Andrew? 10 minutes.
There's a computer, there's a question.
Yes.
Just to quickly comment, I think the main thing here, we calibrate all those devices the same. It's just that distance 3 and lower distance codes, because the boundaries are dominant, they outperform where they should. So we would expect that shift to be a bit smoother at higher distances.
Great. Yeah.
That's probably the dominant effect that we see.
So there are some boundary effects when you're
Essentially the smaller codes are better than they should be, which is what you see smearing in Lambda as well.
Yes. Okay. Right. Okay. So it might be then that if you are not hitting these finite size effects, the lower distance codes would have a little bit worse logical error rates, and it might make this improvement actually a little better. That's a great point. Yeah.
I apologize. This is not a question to you. It's mostly a question to the previous questioner. Which is, might this also be like a product of physical error rate deterioration from increasing the chip size, increasing the number of qubits, getting non-idealities from longer range interactions and frequency packing and that kind of stuff?
We keep all the chips the same and they're calibrated the same. So we use the same qubit frequency, use the same gate calibrations for the distance 3 and distance 7 and all the experiments.
I'm sorry.
I different chip.
Yeah, no, I realized I'm asking a different question than the one you were answering. That's my fault?
Yeah, but have a chat about it.
Yeah.
Yeah, let's chat about that more.
Yeah, I was focused on the switch from 72 to 105 qubit, the two different chips.
Okay.
And the fact that things drifted vertically. That's what I was focusing on, and I think I interpreted the previous answer just completely wrong. So sorry about that.
Okay, I'm going to exploit the fact that lunch is right after my talk. Right, we're not trying to rush into getting well, maybe people are hungry, but I am going to talk a little bit about the other end of this spectrum of hitting these utility targets and where scalability might arise there. Okay, so this is mostly thinking that came out of this early fault-tolerant quantum computing perspective paper that Katerina mentioned. Yeah, and our intent with this paper was maybe twofold. One was to give a review of a number of quantum algorithms that had recently come out that were attempting to tailor themselves to what an early fault-tolerant quantum computer might be. And then second, we were attempting to provide a computational model that might help answer questions about that tailoring. Okay. What do I mean by these early fault-tolerant quantum computing algorithms? So I think a key feature, in my opinion, is that they afford a trade of tolerable error for runtime. So for example, most of these algorithms are aimed at estimation, some estimation task. Picture amplitude estimation, for example. So the FTQC approach to estimation would be that you run a circuit whose number of operations is proportional to the inverse of the target error, estimation error you're trying to achieve. The FTQC approach is that these algorithms afford you a kind of trade-off. The trade-off is that they can use circuits that have fewer operations per circuit, that in principle unburdens or eases the logical error rate requirements, proportional to how many chops you do. But it comes at the cost of an increase in runtime, proportional to that number of chops. This has been referred to as circuit trading. I think that's what we called it in the paper. I actually like this terminology that maybe this recent Google paper introduced, which is circuit division. I think that's more easier to interpret. And if you're interested, here are some example papers that talk about such algorithms for the task of ground state energy estimation and amplitude estimation. Okay. So there have been some challenges raised to these EFTQC algorithms, which I hope we can have some good discussion about. What I see as the biggest challenge to these, I actually haven't heard many people bringing this up, but I think the most reasonable challenge is that, hey, as we saw in Nicole's talk, quantum computers are already taking so long, like we're not going to be able to afford to crank up the runtime, right? That's going to kill the utility. So to me, that seems like the biggest skeleton in the closet here. I've also heard some challenges that like, hey, you don't actually get a easier logical error rate that you have to hit. You should take into account the fact that there's some bias that gets introduced, and it might be the case that these smaller circuits themselves also have to have a very small per circuit error rate, so you don't get a good trade-off. The same criticism also mentions that, hey, maybe error mitigation can help to address that. And actually, I think that's true. Some work that we put out in PRR contains some fairly arduous calculations that are trying to establish how error mitigation works within these algorithms. Okay, the one I want to focus on is in fault-tolerant, here's a criticism that I've also heard. Hey, in fault-tolerant quantum computing, just use bigger chips. That's going to be a way more efficient error time trade-off, right? It's like a, pay some time costs, exponential reduction in error rate. Pay some time and space cost. You don't want to do these kinds of linear trades. So I think that is actually a fair criticism, and it might be the case that you don't want to do these kinds of linear trades that these algorithms afford. The question we were interested in this paper is, can we propose a model where we can distinguish when that is and is not the case? Okay, so going back to this plot, what do these circuit division algorithms afford you? In principle, they allow you to ease the logical error rate requirements, though at an increased runtime cost. And so, remember this criticism is like, hey, just increase the scale. That'll be a much more favorable trade-off. So if indeed bigger systems are providing a proportional improvement in this logical error rate, logical qubit trade-off, then yes, that is totally the way to go. You should consider a bigger chip so you don't have to pay this potentially exorbitant runtime cost. You can move it down to this, the shortest runtime target.
Yeah.
Yeah.
Question.
Yeah.
So I'm curious that why it happens that if you increase this circuit divisions, the total runtime will increase. Do we have any evidence about this?
Oh, you're asking, okay, why do we think that the runtime increases? Maybe we can talk more about this, but maybe just, off the top of my head, I think a decent answer could be that each shot is giving you less statistical power. Each shot, the data is less sensitive to the parameter you're trying to estimate. And so you need to then gather more data to realize the same accuracy.
I can understand that since your circuit depth becomes shorter, then you definitely need to run more iterations to get more information. But if you really sum up the total runtime, they might just be very similar to each other. Right. So, because each of your tests will cost much less runtime, and if you just sum them up, so.
Okay. Maybe something I didn't emphasize is that the number of shots grows as k squared here. So that's why it's like a 3 by 3 in this example. And that's because of central limit theorem.
Right. So I think that's the point I want to bring. So at least for the ground state energy estimation problem, if we have a good overlap, I do believe the number of shots can grow like 1/k. So we can do it.
Okay.
Yeah. So I can share this with you. Yeah.
Okay.
I do think it's possible.
Is this using like soft decoding information?
No.
Okay.
So it's just some good classical signal processing technique, and we can bring it down to 1/k.
We should. I don't know if we've ever fully hashed this out. Yeah, I know what you're referring to. We should talk more about that. It's a little bit. Yeah. Okay. So just to conclude, maybe it's not surprising, if scalability is limited, and this bunching phenomenon is occurring, this might be a case where, as long as the runtime is not too high, you're warranted in using this circuit division technique so that you can hit these utility targets. Okay. So I'll just wrap up. So right at the beginning, I motivated the question, or I said the question I'm most interested in is, how does the logical error rate, logical qubit trade-off depend on system size? Are you getting proportional gains? This is a way to gauge scalability. Thinking about scalability today, I'm very interested to see in these, I imagine there are going to be many of these demonstrations coming out over the next few years, if we can find evidence for certain systems being more scalable than others. And then, looking to the future, I think there's an opportunity to come up with better models for these early fault-tolerant quantum computers, and to co-design algorithms with those, models of these early fault-tolerant quantum computers. That helps us understand what scalability requirements are really needed in order to hit utility targets. So yeah, with that, thank you, and thanks for all the questions.